Hi kids, video 18 is on Newton's second law, which is an equation and also a very important central idea that you'll keep coming back to if you take more physics. The essential question is, what causes objects to accelerate and what relationships determine how large their acceleration is? So in the previous units we talked about what acceleration was, the what, and now we're going to be talking about the why do objects accelerate. So let's go through a little quick review of acceleration. Acceleration, which is the variable a, is the change in an object's velocity over time. Change is underlined there because it's that delta v that matters. It's not the actual velocity, but how much it's changing that makes an object accelerate. The equation that we derived earlier was a equals delta v divided by delta t. And just as a reminder, that means that there is a linear relationship between acceleration and delta v. Because it's on the top of that fraction. So a larger acceleration means an object's velocity changes more. There's also an inverse relationship between acceleration and delta t, which means that a lot of acceleration happens when an object changes velocity in a very small amount of time. So let's do a quick little thought experiment to try to figure out the why that I mentioned earlier. Why do objects accelerate? If you imagine you have a box sitting on a desk and you want its velocity to change, you want to speed it up and make it do something more interesting than just sit there, how many different ways could you make that box change speed? The first thing most people think of is give it a push. Sure. You could pull on it, you could drop it, or you could do something weirder like drag it by a string or even attach a magnet to one side of it and pull it. Or if you've got a hose nearby, give it a good squirt and that's going to cause it to move as well. So hopefully you realize that all of those methods of making the object change velocities had something in common. They were all forces. So in physics we say that forces cause objects to accelerate. The definition of a force is any interaction, like a push or a pull or anything touching each other in contact between two objects. We'll be using a new symbol, which is a capital F, to represent forces, and you'll see lots of little subscripts, just like we did with energy, to indicate what kinds of forces we're talking specifically about. The units of force are the Newton, capital N, which is the same as a kilogram meter every second squared, but we write Newton almost always just to make life a little bit simpler. It's important that you have a sense of how big certain amounts of forces are. So if you imagine a refrigerator magnet, how hard it is stuck on the refrigerator, that would be about 1 Newton of force. The pineapple, if you're holding a pineapple, the amount of force it exerts on your hand would be about 10 newtons. So back to our friend, the 1 kilogram pineapple, the amount of gravitational force acting on it is 10 newtons. Give someone a high five, it's probably about 100 newtons. And if you drop a piano on your foot, that would probably exert about 10,000 newtons of force on your foot. So forces are the direct cause of acceleration, but what relationship should appear in the acceleration equation, or a new acceleration equation, which is known as Newton's second law? Well, the first thing we've already discussed is that force relates to acceleration, and it's probably intuitive to you guys that if you push harder on something, it's going to accelerate more. So we've got a linear relationship between the amount of force exerted on an object and how much it accelerates. There's a second relationship, which has to do with the amount of mass an object has. And you can probably picture that an object with a very small mass is much easier to accelerate than an object with a very big mass. So the more mass an object has, the less it will accelerate, which means there is an inverse relationship between mass and acceleration. If you picture the forces causing this child on a sled to be accelerated, the harder you pull on the sled, the more it's going to accelerate, or the more friction the snow is acting on the sled, the quicker it's going to slow down as well. And the bigger the child is, the smaller the sled will accelerate. So it's harder to get that sled going if you have a very large child in it or two children. So when you put those two relationships together, you come up with this new equation for acceleration. We've got the linear f on top and the inverse m on the bottom. One thing to note is that there's the sigma sign before the f, which means what we really care about is the sum of all the forces acting on an object, not just each individual force. So that'll come into play when we talk about free body diagrams in the next video. But this is our Newton's second law equation, A equals sigma F over m. Put a big box around that in your notes. It's really, really important in terms of all of the physics we'll cover for the rest of the year. So now we have this new equation, Newton's second law. What can we do with it? Well, something kind of interesting happens because we now have two equations for acceleration. And that is that we can actually make a whole bunch of new equations by combining them. And these new equations let us make lots of predictions about how forces and motion interact with each other. So our old equation is A equals delta V over delta T. Our new equation is A equals sigma F over m. So you can put those guys equal to each other since they're each equal to A, and we get this delta V over delta T equals sigma F over m. Now to see the new equations, what I like to do is to rearrange those variables algebraically so that you have a new equations that solve for one variable, so isolate one variable. Like for example, if you multiply both sides by delta t, you get this equation delta V equals sigma F times delta T over m. That's the equation that we used when we were talking about our marshmallow launchers to try to help us make predictions about changes we could make to cause the marshmallows to have a bigger change of velocity when they're launched. You can also rearrange the equation a different way to solve for sigma F. So by multiplying both sides by m, we get this sigma F equals delta V times m over delta T, and we'll be playing around with that form of the equation in the lessons that follow and seeing why those relationships make a big difference in lots of everyday scenarios. Okay, so to wrap up the video, please revisit your essential question, which was what causes objects to accelerate and what relationships determine how large their acceleration is, and go ahead and answer that question in your own words in your notebook. Thank you for watching.